Hello. I came from the DMVGL. I am an engineer, basically a safety engineer at the DMVGL. We have an office in Houston, Texas, and we are in oil and gas business. So today I'm going to talk about HPC applications, let's say. So we used Nimbix cloud system, cloud computing, for a couple of our studies that we have conducted through CFD. So my background, I was a PhD student at Georgia Tech, and I had a structural engineering background, did fluid structure interaction, kind of get familiar with CFD and fluid mechanics during my PhD. And 2 years ago, I joined the DMVGL. Now we have a riser and flow line section that we do independent analysis and verifications for subsea equipment. That is our first time in HPC user forum. So I will first talk about the DMVGL as an organization. Probably most of you guys you don't know or you have little idea of what we are doing. Then we'll move to Nimbix cloud solution that we have used for a couple of applications. And our CFD fields of expertise on pipelines and risers, multi-phase flow, vortex shedding, marine structures. So I will talk in detail. Then I will basically show some showcases through some selected projects that we have conducted. DNV, legacy DNV was headquartered in Oslo, Norway, and GL was headquartered in Hamburg, Germany. So they have merged in 2013. So they include a couple of other companies like Kema in energy, Noble Denton and in maritime, and Garatasan for renewables and energy. Now the company is called DMVGL. The DMVGL is an independent organization, so it's basically we are third party and verification. We do qualify for technology. So we are in different units: maritime, ship hydrodynamics, stability, this kind of stuff, and transportation. Oil and gas, either topside from bottom of the sea floor to top side of the structure. Energy, renewables, wind. You can just think about wind turbines and wind farms. Business assurance, and DNV also has softwares. So they have been using it for maritime and oil and gas business. They are based on potential theory, not computational fluid dynamics. So DNV is a unique organization that invests 5% of its revenue into research and development each year. The DMVGL has been around for 150 years in the certification business. We have 350 offices around the globe, and now after the merger with GL, the DMVGL has around 16,500 people. Let me briefly talk about Nimbix Cloud. So we had to run CFD studies, and of course for big scale studies, so we didn't have that time the engineering or the computation power. Although we have the softwares, we didn't have the hardware. So we have chosen to use Nimbix Cloud because it was easier for us. They have a cloud operating system called Jarvis, where you can basically run your jobs in batch mode or interactively. So it's a software as a service company for end users, so point and click applications. Nimbix has currently 1,200 cores. There are 16 cores per node, and each node has 64 GB RAM. So through Nimbix Jarvis program, we are able to run CAA softwares like ANSYS Fluent and CFX for CFD and Star CCM for CFD. Then we have Nasran and Abacus for FEA and ANSYS Mechanical for FEA. So those things are important because in subsea environment, when you are looking into behaviors or structures, there's a vibration. So you have to couple CFD and FEA through a fluid structure interaction. Focus area first is the pipelines and risers. Risers are basically, again, pipelines that takes the oil from the sea surface and basically carries to the top surface of the floating platform. So there is a growing desire to install subsea equipment on deeper depths with basically loose support, which accounts for temperature effect changes and well growth. So when you have longer and deeper seas, like now we are talking about 10,000 feet of sea depth, so the riser length is increasing and it's very susceptible to vibration due to ocean currents and due to the motion of the topside platform. So vibration is very important because it may, the vibration may induce fatigue at the end of the day, which may cause collapse of the structure. So you can see here on top right side, so this is an example of the vortex in this vibration. So this is a free vibration. Basically, the cylinder is moving in free motion, and the CFD solver and the equation of motion, which is a structure solver, is coupled in two-way. So vortex in this vibration occurs when the vortex shedding that sheds the vortex shed around the structure, there is a frequency of the vortex shedding. So when this frequency of the vortex shedding equals to the natural frequency of the structure, then structures start moving, basically vibrating. This is very important because this may, cyclic vibration may cause fatigue to the structure. So this is based on basic external flow, and you can think about cylinders in tandem. So those can also vibrate. But you have also flow in this vibration. So there's also flow inside the pipe, right? The oil or the hydrocarbons. So when there's a slug flow coming into the jumpers, subsea jumpers, then the structure can also vibrate. So those vibrations are coupled using CFD and FEA solvers together. Multiphase flow. So the multiphase flow includes multi-component of flows, basically. So you can have gas liquid, you have external flow and internal flow. So if you look at the system flow assurance, if you are trying to find out and investigate the ascent integrity of your pipeline, because you don't want to stop the production, right? So when the oil hydrocarbon gets into the pipe, there are other problems that are occurring, for example, erosion or corrosion. So you are able to basically model those problems and assess the forces and basically mitigate the problems using CFD by introducing better designs. So on the right top, you can see that a gas plume study that we have conducted. So the objective of this study was to assess how a gas plume formed after a gas leakage from a pipeline under the seabed can affect the stability of the structure. On the bottom left, you see again gas leakage from a high pressure pipeline to the ambient atmosphere. So vortex shedding is our core business, and where our strength is, basically. So accurate predictions of structural integrity require accurate predictions of the loads on the structure. So it is highly skilled. It requires highly skilled hydrodynamics professionals, and the DNV is a very advanced developer and user of all types of softwares for predicting vortex shedding. So vortex shedding is maybe happen on as simple structure like a cylinder, but the vortex is pretty much highly complicated to investigate because of the turbulence and turbulence boundary layers at different speeds of the current. Then, if you look at a complicated structure like a blowout preventer, assessing the hydrodynamics of this structure is also important. So because this blowout preventer is sitting on the wellhead, you don't want basically a well blowout. So there's a huge structure sitting on the wellhead, and you have to basically calculate or assess in the design the added mass forces or hydrodynamic forces acting on the structure. You can do design improvements using CFD. So you can see a picture of rudder design with different geometries, with different flow conditions. You can basically propose different designs of structures. So one of the other focus areas are marine structures. So you can see that this is a simulation on the bottom right, on a semi-submersible sitting on the seabed. So this is basically susceptible to nonlinear waves. Yeah. So in this study, we are to investigate the shallow water, basically diffraction wave forces on a large-scale structure. So the ENVI, as I said, the ENVI has also softwares using potential theory, and using that softwares and coupling with computational fluid dynamics, we were able to assess the lifetime extreme forces acting on this structure. It is very challenging because this requires shallow water, basically shallow water wave forces. On the right top, you can see a vortex in this motion. Imagine a big structure spar, huge diameter. Again, those vortex can basically cause unstable behavior to the structure. So this phenomenon is called for offshore structures, vortex in this motion. So which is also basically important in assessing moorings and risers life extension, because moorings and risers are connected to these spars. On the bottom left, you can see a visualization of viscous roll motion. Basically, this is 1 degree of freedom motion of a ship and interacting with the wave forces. So in the middle, bottom is a CFD study to assess the wind velocity streamline, the Chesapeake Light Tower, which is close to here. So the NVGL has conducted a preliminary study for a vortex-induced vibration of an M-shaped subsea jumper. We have conducted this study because our client ExxonMobil approached us for this challenging problem. Basically, they have run an experiment case. Let me just write this. So these subsea jumpers are connected to the Christmas trees or subsea blowout preventers. So ExxonMobil has run tow test for VIV response of this subsea jumper under uniform current, and they have experienced vibration. So this was a first and only first of a kind model test so far on the jumpers. What we have done is that we have done an initial study to basically validate the experiment work with the CFD. So we have used software called Star CCM and coupled with Abacus FEA solver and tried to estimate the vibration amplitude. So this was an initial study. This is an undeformed geometry of the jumper, and this is the deformity with the stress magnitudes on the jumper is shown on the figure. So when the current is affecting or hitting the jumper. Another study, again, a blowout preventer. Blowout preventer is a piece of safety equipment that is used to circulate kicks and control the pressure of the valve. So basically the kick is commonly used to describe a phenomenon due to pressure difference when a high pressure formation is reached. And this basically generates an unfavorable pressure gradient that causes an influx of the fluid. So blowout preventer is basically, as the name implies, is sitting there to prevent these kicks and prevent the blowout. So a typical blowout preventer, if you say this is the Deepwater Horizon accident after BP's investigation, so it was a 16-meter tall, maybe, or 54 feet, so it's 4-story high blowout preventer. Those structures are around 300 tons sitting on the, basically, wellhead. So they have we have found out that the BOPs have significant dynamic response. Those investigations done after these accidents. And at that moment, there was no efficient methodology to assess the forces on these blowout preventers. So one way to assess is, of course, you run a CFD analysis, but post-processing is also important because the net force acting on the structure is a combination of added mass, which is the inertial component of the force, and the drag force, which is the basically viscous forces acting on the structure. As you see on the left, the blue parts, this is the original geometry that we got from the client, and this is pretty much complicated. There are lots of bolts and lots of holes. There are lots of spaces that you don't need for a CFD analysis. So basically, you have to simplify and make a watertight geometry for an input for a CFD analysis. This last talks about the geometry preparation. Once we have a watertight geometry, then you need to basically put into the solver, CFD solver, still you are in a pre-processing stage, but mesh it. So by meshing it, you start meshing with the surface. So you have to capture enough detail in the geometry so that you have an accurate representation of the flow, so that you can have a better estimation of forces on the structure. So this example is about 3 million surface cells. It looks like all black, but it's a very fine resolution to capture the details of the structure. So initially we have done 12 million cells when you talk about the domain, that's all the fluids around the structure. But now then we have extended to 70 million cells. Then we start using and exploring how we can run this, because we didn't at that time hardware. We didn't have that time CPUs, so we approached Nimbix and used their cloud solution. We use up to 1,000 cores, and for a steady case, it takes around 3 hours, but for an unsteady and moving structure deformation, it took a couple of days. So post-processing, there's some flow visualization. So this is a complex structure, but the flow around is also complex, depending on the current acting on the structure. So you have a highly turbulent flow. And the flow is also interacting with the structure. So the vortex that's caused from one part of the structure is basically merging with another vortex structure of the other part of the domain. So on the left, this is the velocity magnitude, and on the right is also the velocity magnitude from a different angle of the view. You can again notice that there's a high velocity and around the wall inside, and it's causing some vortex, and vortex are basically interacting inside. So vortex induced motion, when it comes to a platform, and platform moves due to vortex, they call it vortex induced motion. So this is a published data, and we have also published in one of the OME conferences, and validated our CFD work against experiment. Again, VIM occurs as a consequence of exposure to strong current, especially such as like loop currents in the Gulf of Mexico are known to be very high. And VIM is one of the critical factors in the design of mooring and riser systems. So the paper describes a set of VIM CFD simulations in different scenarios. So the current is acting at 30 degree, 60 degree, and 90 degree toward to the spar. There are 3 scenarios. So radius velocity. Radius velocity is a function of the velocity of this current and the nature frequency of the structure. Basically, you know that at a certain radius velocity range, you may have vibration. So for a pipe, for example, radius velocity 4 to 8, you can have a vibration. But for complicated, when the structures are getting complicated, the physics are also getting complicated, so you cannot represent a spar with a pipe, basically, because spar has all those other strakes around it and other apparatus that may change the place of the boundary layer. So this is a benchmark against the model test, Chevron conducted the model test, and they have published a paper. So at the end of the day, what we have is that we got their geometry and run CFD results, CFD simulations. We have used star CCM, and with star CCM, we were able to use the overset mesh physics so that you are able to keep track of the motion of the structure. So mesh is keeping track of the structure. We also use dynamic fluid body interaction. So this simulation did not require the finite element. It is just CFD standalone. So we only concentrate on the getting validation on the magnitude of the vibration. We have used three mesh sizes with a base mesh of 12 million cells, coarse mesh of 6 million cells, and a finer mesh of 30 million cells. So we have decided to use base mesh, where we have run first flow around stationary spar, and so that we don't have change in the forces with the base mesh and the fine mesh. You can see on the right the velocity contours and the pressure contours at a heading of 30 degrees for a radius velocity of 7. So the contours are extracted from 3 layers throughout the spar via spar structure. You can see especially large vortices behind the structure and low pressure field behind it. So we also have plotted a comparison. So the total test results are shown in blue. And they have also, Chevron also published a paper on the CFD in 2007, and they have some deviation from the experimental model test data. But with the base mesh that we have used, we were able to predict the tendency, especially after higher radius velocity, there is a decrease in amplitude. So we were able to capture using CFD. So we use Spalart Alamar's DS model to capture the vortex in this motion. This is a gas plume stability problem. As I mentioned in the earlier slides, the objective is to assess how a gas plume formed after a pipe leakage from a pipeline on the seabed will impact the semi-submersible stability or operation. What we have done is that we have considered 2 different positions for the inlet of the pipe. So this is the whole domain, and there is a pipe leakage. Gas plume is coming from bottom of the sea surface. So there are 2 positions that we have considered. So it is either on the right side of one of the pontoons, or it is just below the middle of the pontoon. Yeah. We have used an Eulerian volume of fluid method to capture the multiphase flow. What we have done is that after running this simulation of CFD, we take the forces and we did a dynamic analysis using one of the potential theory solvers. So DNV has different HPC centers, one being in Hamburg and the other being in Oslo. Hamburg has 7,000 cores and Oslo has 2,000 cores. Those computers are dedicated to basically computation fluid dynamics. And in Houston, we recently got an approval to have a 1,200 core Cray. So hopefully we will be getting and running simulations, safety simulation on this cluster. Again, we are expertise on fluid structure interaction and hydrodynamic load analysis. And That's all about today's presentation.